Welcome back to UST 107. This week we are on Chapter 4, Loading and Performance. We're going to explore how aircraft stay in the sky and how we keep them safe, stable, and efficient while doing it. We'll begin with the control systems that allow pilots to command flight and move into how we measure performance, manage weight, and understand the physiological and mechanical limits of both machines and humans. So we'll be learning flight control systems in fixed wing first, and then we're going to move to helicopters and then into drones. So fixed wing flight controls, you have your primary and your secondary. Primary controls are like the limbs of the aircraft. You have your ailerons, your elevator, your rudder, and the secondary controls are the fine tuners. Flaps increase lift at lower speeds, trimmed tabs reduce pilot workload, and spoilers help descend or slow down. So ailerons are like a seesaw on the wings. One side goes up and the other side goes down and the plane rolls. So ailerons control the roll, which means they tilt the airplane left to right, tipping your head, like tipping your head to one shoulder. They're located on the outer trailing edge of each wing, one of the left wing and one on the right wing. When pilots move the control stick or the yoke left, the left aileron goes up and the right aileron goes down. This causes the left wing to drop and the right wing to rise, rolling the aircraft to the left. Reverse the motion and the plane rolls to the right. Elevators are like nodding your head, pull back to look up, push forward to look down. So the elevator controls your pitch, which means it raises and lowers the nose of the aircraft. It is mounted on the horizontal stabilizer at the tail of the aircraft. Pulling back on the yoke or stick raises the elevator, which pushes the tail down and lifts the nose up. Pushing forward lowers the elevator, raising the tail and dropping the nose. The rudder controls the yaw, which means it turns the aircraft left or right, like shaking your head no. It's mounted on the vertical stabilizer, the upright fin at the tail. Pressing the left pedal moves the rudder left, pushing the tail right and turning the nose left. Pushing the right pedal moves the rudder right, pushing the tail left and turning the nose right. On your fixed wing aircraft, you have your primary flight controls and you have your secondary flight controls. The primary flight controls consist of your aileron, your rudder, and your elevator. The aileron controls your roll. The rudder controls your left to right, which is your yaw. And the elevator controls your pitch, which makes you go up and down. So the aileron is located on the back of the wing, closer to the tip. If you go up on your left side, you'll go down on your right. If you go up on your right, you'll go down on your left. This is what makes you roll. That mixed with the rudder, which makes you go left to right, is how you perform banks. Then of course your pitch is just right below your rudder. The secondary controls consist of your flaps, which is on the inside, closer to the cabin, back of the wing. This slows you down. And on the very back, on the back of your elevators here, I don't know if you can see, but this is where you would fine tune turning the nose right. So helicopters are different beasts. The cyclic is like a joystick. It tilts the rotor disc to move forward, back, or sideways. The collective is your altitude lever, changing blade pitch to climb or descend. The anti-torque pedals, they counteract torque from the main rotor, keeping the nose pointed where you want it. So the cyclic is like tilting a spinning dinner plate. It leans the whole aircraft in the direction you want to go. It changes the angle of the rotor blades as they spin, causing the helicopter to lean and move in that direction. The collective is your lift lever, like turning up the volume on how much lift the blades produce. Pulling up on the collective increases the pitch in all the rotor blades at once. This creates more lift, causing the helicopter to rise. Pushing it down reduces lift, and the helicopter descends. Torque pedals are your tail rudder. They keep you from spinning like a top. The main rotor creates torque that wants to spin the helicopter's body in the opposite direction. The tail rotor pushes against that spin. Pressing the left pedal increases tail rotor thrust to turn the nose left. Pressing the pedal turns the nose. Pressing the right pedal turns the nose right. So in a helicopter, you have your cyclic, your collective, your throttle, and your anti-torque pedals. Your cyclic is going to be the joystick that's between the legs in front. That's your direction, moves you forward, backward, left, and right. Your collective, if you were the captain of the flight, then you're on the right side, so your collective will be on your left. If you're the co-captain, then it'll be on your right. And the anti-torque pedals are just like the rudders for an airplane. Then your throttle is located on the ceiling between the engine levers. So if we go ahead and make sure that's up, and we can start this up, I'll show you what it looks like from the outside. Okay, so it's going to want to spin one way, so you want to adjust your anti-torque pedals to keep you from spinning with it. Your cyclic, it's kind of like a plate on a stick. You move the stick forward, and the plate will move with it. This is your direction. You can go forward, backwards, sideways, any direction. And your yaw, of course, is your left and right. And then your collective tilts everything together to make you go up or down. The nose right. Drones simplify things. No cables, no hydraulics. Instead, they rely on sensors and software. Your inputs are interpreted by a flight controller, which adjusts motor speeds to maintain balance and direction. It's like flying it with invisible strings pulling the code. So you have electronic stabilization via gyros and accelerometers. Inputs, you have your throttle, pitch, roll, yaw mapped to motor speed. It's all digital. So while they may look simple, they're like flying computers with finely tuned control systems. Unlike airplanes and helicopters, drones don't use cables or hydraulics. They rely on sensors, software, and motor speed adjustments to stay balanced and respond to commands. Most drones, especially quadcopters, respond to four main inputs. Throttle, which makes the drone go up and down. Pitch, tilts the drone forward or backward. Roll, tilts the drone left or right. And the yaw rotates the drone left or right. These controls are usually managed by two thumbsticks on a remote controller or app interface. To fly safely, we need to know how fast and how high we're going. Airspeed is measured by comparing dynamic and static pressure. Altitude is derived from barometric pressure. And the VSI tells us how quickly we're climbing or descending, critical for controlled flight. So, airspeed indicator measures how fast the aircraft is moving through the air, not over the ground. It uses a tube, a small forward-facing tube, to collect air pressure as the plane moves. Compares this dynamic pressure to static pressure. The difference tells the system how fast the air is flowing past the aircraft. Imagine sticking your hand out a window of a moving car. The faster you go, the harder the wind pushes. That's what airspeed indicator feels. It measures the push of the air against the aircraft. To fly safely, we need to know how fast and how high we're going. Airspeed is measured by comparing dynamic and static pressure. Altitude is derived from barometric pressure, and the VSI tells us how quickly we're climbing or descending, critical for controlled flight. So airspeed and altitude instruments. We have an airspeed indicator, which measures dynamic pressure. Altimeter uses static pressure. Vertical speed indicator is your rate of climb and descent. These instruments help pilots answer three critical questions. How fast am I going? How high am I? Am I climbing, descending, or level? The airspeed indicator measures how fast the aircraft is moving through the air, not over the ground. It uses a tube to collect the air pressure as the plane moves. Compares this dynamic pressure to static pressure. The difference tells the system how fast the air is flowing past the aircraft. Imagine sticking your hand out of a moving car window. The faster you go, the harder the wind pushes. That's what airspeed indicator feels. It's measuring the push of the air against the aircraft. Airspeed is not ground speed. A strong headwind can make you feel fast in the air but slow over the ground. Altimeter tells you how high you are above sea level. Measures static air pressure, which decreases as you go higher. Converts that pressure into altitude using a calibrated scale. Pilots set a reference pressure called the altimeter setting to ensure accuracy. Think of climbing a mountain with the barometer. As you go up, the air gets thinner. The altimeter reads that change and tells you your elevation, like a ruler that stretches into the sky. Weather affects pressure, so pilots must adjust the altimeter setting to stay accurate. Vertical speed indicator shows how fast the aircraft is climbing or descending, usually in feet per minute. Also uses static pressure, but with a delayed response. Compares current pressure to slightly older pressure. The rate of change tells the VSI whether the aircraft is going up, down, or staying level. Imagine walking up or downstairs with a pressure-sensitive backpack. If the pressure drops quickly, you're climbing fast. If it rises, you're descending. The VSI is the backpack. It senses the rate of altitude change. There's a slight lag, so pilots use it alongside other cues like pitch and power. So how they work together. Airspeed keeps you flying safely, not too slow and not too fast. Altimeter keeps you clear of terrain and in the right airspace. The VSI helps you manage smooth climbs and descents. Speedometer equals airspeed if you think of it like driving. GPS, elevation, altimeter, and hill grade meter, VSI. So loading, weight, and balance. Think of center gravity like the balance point on a seesaw. If it's too forward, you struggle to lift the nose. Too far back, and the aircraft becomes twitchy and unstable. In drones, center gravity affects hover stability and battery efficiency. So center gravity is the point where the aircraft's weight is evenly balanced. It's measured from a reference point, usually the nose or the firewall, and must stay within a safe range. Too far forward, the nose is heavy, hard to lift off, or flare during landing. Too far back, the tail is heavy, aircraft becomes twitchy, unstable, and prone to stalls or spins. Each item, passenger, fuel, cargo, has a weight and a location. We multiply those to get moments, add them up and divide by total weight to find the center gravity. If the center gravity is wrong, you'll have poor handling. Aircraft may feel sluggish or overly sensitive. Reduced performance, climb rate, fuel efficiency, and stability suffer. Safety risk, in extreme cases, the aircraft may be uncontrollable. If a drone's battery is mounted too far forward, it may tilt and drift. If a payload is uneven, motors work harder, reducing flight time. So what is load factor? Load factor is a measure of how much extra weight the aircraft feels during a maneuver, especially in turns, climbs, and turbulence. It's expressed in g-forces. G equals gravity. 1g equals normal weight, straight and level flight. 2g equals the aircraft feels twice as heavy. 3g equals 3 times as heavy, and so on. This matters because aircraft are only built to handle a certain amount of stress. Exceeding those limits can cause structural damage, or worse. Load factor increases in a steep turn. The wings must generate more lift to keep the aircraft from descending. That extra lift equals extra load. In turbulence, sudden gusts can momentarily increase g-forces. In pull-ups or abrupt maneuvers like recovering from a dive, even though the aircraft's weight hasn't changed, the forces acting on it have. Structural limits. Every aircraft has a maximum G load it can handle. Exceeding it risks bending or breaking parts. Stall speed increases. The more G's you pull, the higher your stall speed becomes. Pilot awareness. You may not feel it in a gentle turn, but the aircraft will. So an example, in a 60 degrees bank turn, the load factor is 2 Gs. That means a 2,000-pound aircraft now feels like it weighs 4,000 pounds. The wing must produce twice the lift to maintain altitude. Okay, so stalls equals exceeding critical angle of attack. It's not about the speed, it's about the angle. So it's not engine failure. They're aerodynamic breakdowns. When the wing exceeds its critical angle of attack, airflow separates and lift vanishes. So to recover, it's pretty simple. Lower the nose, add power to regain airflow. For drones, stalls are rare, but it can occur in a fixed wing model. So several factors influence performance, like weight. Heavier aircraft need more lift and longer runways. Altitude. Higher altitude means thinner air, less lift and engine power. Temperature. Hot air is less dense, reducing performance. Headwinds help with takeoff and landing. Tailwinds can make them harder. Runway surface and slow grass or uphill runways increase drag and reduce acceleration. These factors combine into what pilots call density altitude, a measure of how thin the air feels to the aircraft. So like flying in heat or in high heat in altitude is like running uphill with a backpack. You'll get there, but slower, sweatier, and with less margin for error. So drones are also affected by the payload. The weight reduces flight time and maneuverability. Battery health affects climb rate and endurance. Wind can destabilize hover and drain power faster. Autonomous drones often adjust for these automatically, but manual pilots must. Poor performance can mean longer takeoff rolls, slower climbs, or an inability to clear obstacles. In emergencies, performance margins are life-saving. For drones, it affects flight time, stability, and mission success. So physiology, remote pilots must evaluate their physical and mental fitness for flight. Factors that would interfere with safe SUS operations are dehydration, heat stroke, hypothermia, stress, fatigue, acute fatigue, and chronic stress. So pilots are part of the system. Hypoxia can sneak up above 10,000 feet. Spatial disorientation can flip your world upside down in clouds. A lot of the crashes are because the spatial disorientation, fatigue dulls reaction time. Even drone pilots need rest, judgment, and everything. The brain is your co-pilot. If it's foggy, tired, or starved of oxygen, you're flying blind, even with perfect instruments. So maintenance and inspection procedures. Maintenance is the ongoing care of attention given to an aircraft to ensure it remains safe, reliable, and airworthy. It includes everything from routine checks to major repairs, and it's guided by strict schedules and regulations. There are two main types: preventative maintenance, which is regular tests to keep things running smoothly, like oil changes or tire checks. Corrective maintenance, fixing something that's broken or worn out. So it's like brushing your teeth. If you skip it once, you'll be fine. If you skip it often, they'll decay. So that is all we have for this chapter. We'll see you next time with operations.